I'm Meghamala, working as an assistant professor from Institute of Aeronautical Engineering. So, coming to today's topic, today I'm going to talk about sequential logic. So, what is the sequential logic? As we are discussing about Verilog as an HDL, here the sequential logic is nothing but it deals with the combinational and the sequential circuits. Okay, so here the computers and the other devices, they also have some memory. So it's all about the logic deals with the sequential and the combinational circuits, where those circuits holds the memory. So we all know that the computer devices and other electronic devices, they hold some memory, right? So that executes a sequence of operations. So the memory, the devices which are holding some memory, they go or else they execute the sequence of operations. So under some situations, so there are nothing but the stored information. The information which is already stored in the memory, based on the memory, the combination or the logical circuits, the electronic devices, they just execute the information or else it just executes the operations, and they are referred to as the sequential machines. This is nothing but sequential machines. So sequential machines, in overall we can say that the devices which are holding the memory, they execute the operations based on the direction of the stored information. So whatever the information the respective devices are holding, based on the memory which the circuits are holding, the execution of the operations takes place based on the stored information, and we are calling it as a sequential machines. And the circuitry model is nothing but the sequential logic. So the model which is with respect to the circuit based on the memory, containing the memory elements, and we are calling such models devices are nothing but the sequential logic. And coming to the second point, sequential machines do not follow combinational logic. Okay, so as we know that here we have sequential logic and combinational logic, we are saying that the sequential machines, the machines which are having the memory elements, the memory, the devices which are holding some memory, which are storing some memory, those are nothing but the sequential machines. And the sequential machines, they do not follow the combinational logic. Because why? Because here we have a reason. Because the output is a sequential machine depends upon the history of the applied inputs, and as well as their present value. So here we are saying that the sequential machines are not to be considered as a combinational logic, because the output of the sequential, for example, if this is a sequential machine, it has some inputs and it has some the outputs. Okay, so here the output, we are saying that the sequential machines are not to be considered as a combinational logic, because the reason is the output of the sequential machines, okay, the output of the sequential machines depends on the present value of the applied inputs, and as well on their present past history of the applied input. That means past input and as well as the present values of the input. So here the output of the sequential machines, we are saying that the sequential machines are not comes under the combinational, they do not follow the combinational logic, because the output of the sequential machines, they depends not only on the history of not only on the past inputs, but as well the present values. Not only on the past input, but as well as the present values. Okay, so because of this reason, we are saying that the sequential machines are they do not follow the combinational logic. And the sequential machines can be deterministic or probabilistic or synchronous or asynchronous. So here we can say the sequential machines. Okay, the sequential machines can be, okay, we can call the sequential machines asynchronously. We can call asynchronous sequential machines. We can call we have the synchronous sequential machines, and based on the probabilistic, the nature of the output that it drives, and as well the deterministic of the output. So here, in all the four aspects, we can say the sequential machines can be called asynchronous, synchronous, and we can predict the outputs based on the present values and as well as the past inputs and as well as the present values. And also we can say it's as a probabilistic nature. Okay, and the last point of the sequential logic is a common clock acts as synchronizing signal for the operation of synchronous sequential machines. So here we have, in order to go for the synchronous, as we say that the sequential machines can also be acts as asynchronous sequential circuits, and we have the synchronous sequential machines, right? So we have two kinds, synchronous and asynchronous. When we call a synchronous sequential machine is when that particular device, if it is accommodated, or else if it is elaborated accompanied with the clock signal. Okay, if a common clock acts as a synchronizing signal for the operation of synchronous sequential machines. So in order to operate synchronous sequential machines, we need definitely a common clock. Okay, so based on the clock signals, based on the clock, how the clock is, each and every clock signal, how the signal is passing. Okay, synchronously the signals will pass. So based on the common clock, the common clock acts as a synchronizing signal. Okay, common clock, the clock which is appended with respect to the sequential machines, such clock signal. Okay, such common clock signal acts as a synchronizing element for the operation of synchronous sequential machines. So here, in the coming classes, we will discuss about the asynchronous sequential machines. Basically, asynchronous sequential machines are nothing but they are the devices, or else the output which is drawn by the asynchronous sequential machines are not with respect to the time constraint. Okay, asynchronously, not in a synchronous wise. Okay, not in a proper signal wise. We see the outputs. Output will be generated asynchronously based on the irrespective of the time constraint. So such devices or such machines are considered to be as asynchronous sequential machines. But whereas the clock signal, when the common clock acts as sequential machines, based on the sequential for synchronizing purpose, we'll use the common clock signal. This common clock signal only can be used in terms of, or else in order to operate the synchronizing sequential machine purpose. And then we'll see about the storage element. So what is the storage elements? We all know basically logically if we talk about the storage elements are nothing but the devices which store some information, isn't it? Which store some information, or else the memory devices which store some memory, some kilobytes or megabytes, some kind of memory. If certain device is storing, okay, we are calling such devices as storage devices. Particularly coming to the storage elements. Storage elements are nothing but they store some information based on the binary bits. Okay, so here the storage element, they store the information in the binary format. So in the binary format, the devices they are storing some information. Then such elements are nothing but the storage elements. So usually when it comes to the storage elements, the devices which holds, okay, which stores some information, which stores information in the based on the binary bits are pertaining to, or else in kinds of, as we are calling it as a binary bits, they store the information only in terms of zeros and ones. Okay, so the elements which are storing the information in terms of zeros and ones are nothing but the storage elements. For example, we can see here the opcode for addition in a simple microprocessor might be the binary word pattern for 0010, and the circuit that stores information can be level sensitive, edge sensitive, or combination of both. So here, if we ponder on this particular sentence, I can say that we are talking about storage elements, right? So for example, in the microprocessors, in order to store the bits, usually we'll store the bits in terms of opcodes, okay, operational codes. So here, in the operational codes, for example, if certain microprocessor is about to perform the addition operation, okay, so that microprocessor, such kind of microprocessors, if they are generating some opcodes, operational codes, so the operational codes which are generated by the microprocessor in order to perform some addition operation from the pattern, okay, from the word pattern, for example 0010, okay. So from this word pattern, if they wanted to perform some addition operation based on the opcodes which are generated by the microprocessor, the circuit that stores the information. So the circuit, such microprocessor will store the information in terms of in terms of three elements, that is level sensitive, edge sensitive, and the combination of both. So basically level sensitive and edge sensitive. We just talk about this kind of sensitive, level sensitive and edge sensitive of the signal processing based on the latches and the flip-flops, okay, based on the latches and the flip-flops. Why? Because latches and flip-flops are nothing but the storage elements. They store one bit of information. So usually when it comes to the latches and flip-flops, basically the operation of latches and flip-flops can be occurred in three kinds, okay, level sensitive flip-flops, edge sensitive flip-flops, or else sometimes we may see the operation of the latches and flip-flops in both the combination, that is level sensitive and as well as the edge sensitive. So coming to the level sensitive, what is this level sensitive? Level sensitive storage elements are commonly referred to as latches, isn't it? So in the second statement we have discussed, right? Usually the latches and flip-flops will come across the level sensitive or the edge sensitive signal processing. So here the level sensitive storage elements. So level sensitive storage elements usually we consider the latches, and edge sensitive storage elements are considered to be as flip-flops. So we all know what is latches and flip-flops. In the previous classes we have discussed. They are the storage elements where they store one bit of information. And here, coming to the kinds of latches and flip-flops, we say the latches are the transparent devices, isn't it? Latches are the transparent devices. And coming to the categories of the flip-flops, we have different types of categories, different kinds of flip-flops: D flip-flop, toggle flip-flop, master-slave flip-flop, master-slave flip-flop, JK flip-flop, and so on. So here, and the mechanism of such particular flip-flops also we have just discussed. And in the different subjects like different digital logical device design subjects, we can also come across all the design parameters of the latches and as well as the flip-flop. But in this particular topic, in the sequential logic, when it comes to the storage elements, usually we will store the one bit of information on the latch and as well as the flip-flop. So basically, as I said to you, the performance of the operations of the particular storage devices can occur or else can be drawn through the three times, that is level sensitive, edge sensitive, and the combination of both. So here the level sensitive goes with or else commonly referred to as latches, and edge sensitive storage elements are commonly referred to as flip-flops. So the output of level sensitive. Now coming to the output of level sensitive and as well as the edge sensitive. So the output of level sensitive sequential circuits are immediately affected by the change of value of more inputs, one or more inputs, as long as the enabling signal is asserted. So here this level sensitive operation, when we see the level sensitive sequential circuits, in the circuits, the output of the circuits can be affected. When the output of these circuits can be, we see the abrupt changes in the output of the circuits. Why? Because when the abrupt changes occur with respect to the input, that is one or more inputs. So when the values of the input abruptly they are changing one or more values only at the particular inputs. Only at the particular inputs, if one or more inputs are changing abruptly, then we can see there is a change. Immediate effect of changes can be occur in the output. Okay, so this is nothing but the level. In the level sensitive, we see the abrupt changes in the output. That is with respect to the abrupt changes in the input occurring. So whenever the output, if you see sudden change in the output, it means that there is an immediate change in the, there is an occurrence of the immediate change in the input values. Okay, so this is we will be observing in the level sensitive triggering, level sensitive elements, storage elements. Coming to the edge sensitive storage elements. So here Edge sensitive storage elements are nothing but usually we refer to the flip-flops, right? So here in the edge sensitive storage elements, they are these circuits, edge sensitive circuits are sensitive to the values of the input, but the change value only when the synchronizing signal makes either rising or falling edge transition. So here in the edge level transition, in the edge sensitive transition, we are saying that the input values are very sensitive. Okay, why? Because here in the edge sensitive storage devices, usually we will make use of the clock signal. This clock signal will help us for the synchronizing purpose. Only for the synchronizing of the synchronizing purpose, we are setting a common clock signal. Because of that common clock signal, we are saying that the input values are very sensitive. Okay, so we see the synchronizing the changes will only make when synchronizing signals may change either rising or falling edge. So here, as we are considering a common clock signal, we are saying that the synchronizing the effect can be occurred based on the synchronizing signal changes. So based on the synchronizing signal changes, it makes the levels unequal based on the rising. Sometimes based on the signal clock signal that you are considering for the synchronizing purpose, you may see the output may be rising or else output may be falling edge transition. So based on the because of the clock signal that you are setting, that is in the edge sensitive, we are saying that as the inputs are very sensitive, and you may see the output transition changes because of the clock signal that you are considering applying, and that clock signal it can be synchronized based on the signal, and sometimes it may take the falling edge or else the rising edge, or as well as the sometimes measure rising edge and as well as the falling edge. Okay, so such kind of transitions we can see only in the edge sensitive triggering elements. Okay, edge sensitive triggering, whereas in the level sensitive triggering, the output will see the abrupt changes in the output, and that abrupt changes can be occurred only immediately if there is a change in the input values. So this is a bit difference between the level sensitive and as well as the edge sensitive. So coming to the design of sequential machines. So when we if we observe the design of some sequential machines, how the designing part can observe in the sequential machines. Keenly we will discuss about the designing part in the sequential machines, but this is like a just to be considered. So here, unlike combinational logic, whose output is an immediate function only of only its present inputs, sequential logic depends upon the history of the input. So in the previous slide we have discussed regarding the sequential logic. So sequential logic is nothing but the output depends not only on the present value of the input but also the past value of the input. So this is the most important thing to be remembered when it comes to the sequential logic. Sequential elements are nothing but the devices, the devices which holds the output, and the output values that not only depends on the present value of the input, but as well it also depends on the past value, the history of the input, the past values of the input. So this dependency is expressed by the concept of state. So usually in the designing of the sequential machines, whatever the circuit that you are designing, considering the sequential machines, always remember that we use a concept of state. Okay, so in the state, we use the concept of state. We need the state transition mechanism. We'll be knowing more about the state diagram, state to table, and the state transition mechanism. That means what? The transition takes place from one state to the another state. So when it comes to the designing of the sequential machines, we consider the dependency of the inputs and as well as the present value, dependency of the present value of the inputs and as well as the past values of the input. that the present and past values of the input can be transitioned. The transition of such values, such storage elements can be made with respect to the state. Okay, so in the coming slides or else in the coming classes, will be discussed about what is a state machine, what is a state, what is state machine, what is state transition machines, how the state transitions occurs from one state to the another states. Okay, it depends upon the present state and the past input values. So it all can be seen under the state. Then all sequential machines have the general feedback structure in which the next state of the machine is formed from the present state and the present input. So here in the sequential machines, generally the next state will be formed. Okay, so here as we are discussing about the state, we have the present state and we have the next state. So the next state will be formed only based on the present state values, present state input. So here the sequential machines have a logic based on the feedback structure. So this sequential machines, they have a feedback structure. That feedback structures will have the next state and as well as the present state. The next state will be formed only with the help of the present state values and the present state input. The next state is formed only on the present state value and as well as the present state input. So the all sequential machines, they have a feedback structure. Okay, in that feedback structure, you will come across the next state and as well as the present state. The next state values can be the next state is formed based on the present state value input and as well as the present state value, present state input. Next, combinational logic from the next state, from the primary inputs and the stored to the present state. So here the combinational logic forms. How the combinational logic is formed from the sequential logic, because based on the primary inputs stored in the present value. So basically the important thing to be remembered is the next state is always formed based on the present state. How this present state is formed? The present state is formed only on the primary inputs, forms from the primary inputs and the stored value of the present state. So here the next state and present state, they have the storage elements. Okay, the next state and the present state, they have the storage element. They store some information. The next state is formed only with the help of the present state. Why? Because this present state holds the present input and the present state. And the combinational logic based on the sequential machines can be performed or else can be formed based on the present state itself. What this present state is having? This present state have the primary inputs. It has some inputs, right? Present inputs, primary inputs and the stored value of the present state. So this present state consists the stored value and as well as the primary inputs. Okay, based on the stored value and the primary inputs, we could able to get the next state. Okay, next, coming to the state register. What is the state register? Register, we all know, register is nothing but it is also a device where it holds the information, right? We have discussed regarding the registers, different types of registers and how the transition takes place between one register to the other registers based on the register transfer language. Using the register transfer language, we can transform or else we can transfer the data between the registers. That is, the data is transferred between the registers among all the modules can be done using the register transfer RTL, register transfer language. So what is the state register hold? This state registers hold the state, the present state and the next state information. The information of the present state and as well as the next state. The state information can be stored or else can be held in this register, state register. So here a state register is nothing but the memory. Obviously, certainly it is called the memory. The memory which is obtained from the next state and as well as the present state can be held in this state register. So a memory holds a value of present state and the value of the present state, next state. Okay, so the value, this state register, it holds the memory of the present state, present state and as well as the next state, which is formed from the input and the content of the state register. So overall, I can say that the state register is nothing but it is a device where it holds the value or else where it holds a memory or else the information from the present state and as well as the next state. The present state itself consists of the information which is coming from the primary inputs and as well as the stored value of the present state. The values, whatever the states, the present state and the next state, PS and NS, whatever the present state and next state, they are holding the information. The information which is stored in this present state and next state can be stored in overall a register. We are calling that register as a state register. State register is nothing but it holds a memory which is obtained from the present state and the next state. So, block diagram of a sequential machine. So, this is a sequential machine as we are discussing the design of sequential machine. Here, we say they are widely used in the application that require prescribed sequential activity. So, in order to perform the sequential activity based on the clock signal, with the help of the common clock signal, such devices are nothing but the sequential machines. Basically, the sequential machines consist of the next state, logic and the memory. So here, if you observe the next state logic, we have a feedback, right? So the sequential machines always have a feedback and that feedback will have some memory elements. Okay, that memory are nothing but sequential memory elements, latches or the flip-flops. So here we have a memory and this is nothing but the present state and this is nothing but the next state. The next state is obtained only with the help of the present state. The present state, whatever the information that is holding, the present input or the present state, that is given back as a feedback to the next state. Then how the next state is formed. And then from the next state, again it will have some inputs. Okay. And then it give the next state, the memory consists of both the present state and as well as the next state. This is nothing but the state register. State register consists of both the present state values and as well as the next state values. The next state values always, the next state values is formed only based on the present state. The present state inputs, present state input and present state values. Present state input and present state values. So this is about the sequential. It will have a feedback of present state. So the feedback, whatever the output that present state is holding, that output is given back as input to the next state. That's how the next state is formed. And the combination of the information which are present in the next state and the present is nothing but the register, or else we are calling it as the memory. This is nothing but the memory and the register. State register. Another name for the memory is state register. Okay. So, design of sequential machine. The state transition of asynchronous sequential machines are unpredictable. So, coming to the sequential, synchronous, as I said we can, in the sequential machines, the sequential machines can be predictable, asynchronous, synchronous, right? Okay, and they are deterministic. So, these are the characteristics that we see in the sequential machines. So, we say that sequential machines can go synchronous, asynchronous, synchronous and asynchronous. So, synchronous are nothing but based on the common clock signal, the output can be transition. That is nothing but the synchronous. But whereas here in the synchronous sequential machines, we say, we observe the output can be unpredictable. Okay, the transitions of the particular asynchronous sequential machines are unpredictable. Okay, why? Because the common clock signal, the output cannot be transition. The transition of the output cannot be occur as with respect to the time. Okay, the inappropriate time signals can be considered, whereas we are saying that the asynchronous signals or asynchronous sequential machines are nothing but they are the unpredictable machines. But because synchronous machines overcome race issues. What is this race issues? Race conditions. Okay, race conditions we mostly will observe in terms of the memory transition. At times of memory transitions, we observe the rat race conditions or race conditions. So the synchronous machines overcome race issues. They are having a clock period that is sufficient to stabilize the signals in the circuit. we are saying that the race conditions can be overcome. Okay, race conditions are nothing but it is an error formed when the two or more transitions occur simultaneously. When the two or more transitions of the memory, when they are executed simultaneously, we will occur some race conditions. Okay, so such conditions are nothing but the race conditions, and that race conditions can be overcome. As it is one of the disadvantages, we can overcome the race condition with the help of the synchronous machines. Okay, synchronous machines can overcome the race conditions because these synchronous machines are having the clock periods, clock signal, where that is the clock signal itself is sufficient to stabilize a signal in the circuit. So in order to stabilize a signal in the circuit, the clock signals are well efficient and well sufficient in order to overcome the race conditions, race issues. And then synchronous machines are widely used because timing issues are reduced too. So here, synchronous compared to the asynchronous sequential machines and synchronous sequential machines, synchronous machines are widely used because of the timing issues. So we can easily reduce the timing issues because based on the clock signal. So synchronous machines compared to the asynchronous are widely used. And then ensuring the setup and hold timing constraints are satisfied at flip-flops for a given system clock. So here, in the designing of these sequential machines, when the transition of the signal takes place, we come across a hold time, setup time, and as well as the hold timings. So ensuring that setup and hold timings constraints are satisfied for the flip-flops. So here in the synchronous sequential circuits, in the sequential circuits, we ensure that the signal will not go as per the asynchronously, not beyond the time constraint. The signal goes on in a proper way, and that can be achieved with the help of the timing constraint, that is setup time and the hold time and the setup time. So due to this, because of this two time constraints, we can make, or else the output can be modified in the synchronous way. Next, ensuring the clock skew induced by the physical distribution of the clock signal to the storage element does not compromise the synchronicity of the design. So here, as we in the sequential machines, as we are considering the common clock signal, and as we are considering the common clock signal, obviously sometimes, during the transition of the signal from the input to the output, sometimes we can come across the clock skew. So here, the clock skew induced in the physical distribution of the clock signal to the storage elements does not compromise the synchronicity. So here, when you are transferring the data from the input from one device to the another device, obviously in a particular time constraint, the output must acknowledge the input, right? So the output must acquire the input whatever the device is giving out. So that output can be that output which is observed in the output, the signal should be comes in a prescribed format, right? In a prescribed way. So in that format itself, we can say that we will be getting the assurance of the output can be observed at the maximum efficiency with respect to the clock skew. Okay, the maximum efficiency, the output can be observed, and that is with respect to the clock skew. And this is because the common clock is observed. We are discussing about the synchronous sequential machines, right? So as we are pondering on the sequential machines, obviously a common clock is set. Okay, in order to erase or else in order to omit all these constraints regarding to the timing setup. So we say that the output is obviously ensured with respect to the proper prescribed signal with only it is achieved with respect to the common clock signal. And providing synchronizers at the synchronous inputs to the system. So sometimes we may see the asynchronous output. So though we are giving a proper signal synchronously with respect to the different time constraints, but our output, sometimes we see the asynchronous output. So that can also be resolved using this, using the sequential machines, using the clock signals, that can also be resolved. As I said you, the utmost error, the race conditions can also be resolved. They can also be overcome with the help of this synchronous machines. So compared to the synchronous and synchronous machines, most probably the synchronous machines can be preferred first. And then the state transition of the edge trigger flip-flops based on synchronous machines are synchronized by the active edge, that is rising or falling of a common clock. So as we discussed, the devices considered under the sequential machines, they can go to the edge sensitive and the level sensitive, or the combination of both, right? So edge level sensitive is based upon the latches. That means abrupt changes can be observed at the output, and those abrupt changes which are observed at the output are due to the abrupt changes which are observed at the input. That is nothing but the level sensitive triggering. Whereas the edge sensitive elements are nothing but the output can be changed only because of the synchronous way of the signal which is passing, which is transition with respect to the inputs. Okay. So the state transitions of an edge triggering flip-flops can be synchronized machines are synchronized by the active edge. So here, when you are discussing about the edge sensitivity, edge triggering or else edge sensitivity based on the rising or falling edge of the common clock, the transition of a signal can be rising or falling edge of the common clock. So the state changes gives rise to changes at the output of the combinational logic that determines the next state and the output of the machine. So here, because of this edge sensitivity of the flip-flops, that is in terms of rising edge or the falling edge, we say the output, the state changes, the state changes can give rise to the changes of the output. Okay, we see the changes of the output based on the next state and the outputs of the machine. That means what? The output can be changed. We see the state transition between the inputs and the output. That means output can be changed based on the logic that is determined with respect to the next state and as well as the output of the machine, with respect to the next state and as well as the output of the machine. And the clock waveforms can be symmetric or asymmetric. So here in the sequential machines, as one of the most prominent thing that we are considering is a clock skew, common clock signal. So sometimes the clock waveforms can be symmetric or asymmetric waveforms. You will be observing the clock signals to be sometimes in terms of asymmetric and symmetric. And features of an asymmetric clock waveform. So when you observe the features of when you compare the features of symmetric and asymmetric clock signal, the features of asymmetric is mostly the length of the interval in which the clock is low. The length of the interval, see here, the clock low is not equals to the clock high. That means what? The length of the interval of the clock signal, the length of the interval in which the clock is high. That means the length of the interval. For example, if this is a clock signal and this is a clock for the high. So here we can see the length of the clock signal with respect to the input does not match with respect to the output. So this is nothing but the asymmetric clock signal. So the clock signal, the features of asymmetric clock signal is nothing but the interval of the clock signal with respect to the clock low is not equals to the interval of that particular with respect to the clock high. Okay. So if you observe such kind of thing, not equals, if you observe such kind of thing, then we can consider to be as the asymmetric clock waveform. So since this is the asymmetric clock signal, so here this is the rising edge, we call this is the falling edge. So this is the rising edge and this is the falling edge. So this is the time period, actual time period is 1 clock period of cycle, right? So this is a 1 clock period of cycle, 1 clock period of cycle. So this is a rising edge and falling edge where it is a 1 clock period of cycle. 1 clock period of cycle. So most application specific integrated circuits are 6. So in most of the application specific integrated circuits are designed for fast synchronous operation. So for the fast synchronous operation, most probably they'll be using this as they'll be using in the S6. the sequential machines with respect to the synchronous operation can be mostly preferred. And then the period of clock must be long enough to allow all transient activated by the transient of the clock to settle down the output at the of the next combination logic before the next active edge occur. So here, in order to before the occurrence of the next active edge, okay, as we are discussing about the edge sensitivity, right? So before the occurrence of the next edge, what happens is all the transitions will be completed. Okay, if for example, if it's edge 1, edge 2, so before edge 2 is formed, at the edge 1, all the transitions pertaining to that signal, pertaining to that output, pertaining to the input which is given, all the things will be done over at the edge 1. Okay, then only it will pass through the edge 2. Okay, so that is what it says here. The period of clock signals must be long enough to allow all the transitions. So here what it's saying is the period of clock signal must be long enough. Okay, sometimes we see the short periods, right? So the transitions occurs in a short intervals of time, isn't it? For example, T1, T2, T3. So here in the short intervals of time, what happens? The transition takes place. But whereas here, in order to overcome certain race conditions, we are saying that the period of clock must be long enough, just in order to transit all the transitions, in order to complete all the transitions before the next edge arrives. In order to complete all the transitions, the period of clock must be long. The interval of clock signal must be long enough. And the set of state of a sequential machines, okay, the set of state of a sequential machines is always finite, and the number of possible states is determined by the number of bits that represents a state. So here, the set of states are in the sequential machines are always finite. There is no limit. Okay, there is no limit to consider a particular states. So, for example, in order to design some module, okay, the states that I'm considering is to be 10. Okay, but that particular module requires 20 or 30 maybe. So this in some modules they require some infinity. So here we say that there is no particular limit. There is no particular limit for the state. In the sequential machines, there is no particular limit for the state. They can be finite, and the number of the possible states are determined, and the bits representing it. So each and every state holds some value, and that value which the state is holding will help the state to form the next state. Okay, so the machine whose state is encoded as an n-bit binary can have up to 2 power n states. So already when a particular state is having the n inputs, so it can encode 2 power n output states. So that means what? A machine's which state it can encodes, if it is having n power n bits, it can encode 2 power n output bits. And we use this term state finite machines to refer the clock sequential machines that has one of the two structures. So here in the sequential machines, we come across different machines based on some author names like Mealy and Moore. So here we use so when you are considering such machines, we usually refer that particular term as finite state machines. So we say that we have a state of finite states. We can consider the finite states can be considered, and so the name indicates that finite state machines. So the finite state machines is nothing but it refers to a clocked sequential machines. Finite state machines, FSM. Finite state machines are nothing but the clocked sequential machines. That means what? They hold some information based on the changes which are occurring in the present inputs and the past and outputs. The output is transition. So here the name usually will refer as finite state machine, and these are nothing but the clocked sequential machines which has one of the two structures. So those two structures can be synchronous finite state machines and asynchronous finite state machines. So synchronous is nothing but the clocked machines, that is the clocked finite state machines. Synchronous finite state machines, they have widespread of applications. As I said, when you compare The asynchronous sequential machines and synchronous sequential machines, most probably the synchronous sequential machines are preferred first. The priority is given to the synchronous sequential machines. So the synchronous finite state machines have the high priority. That means they go for the high speed of applications in digital systems. Okay, in digital systems compared to the asynchronous, synchronous sequential machines go with the high priority. For example, data path controllers in computational units and processors. So here in the process, in the various multiprocessors and multi-controllers, we see that the finite state machines are widely used. And synchronous finite state machines are characterized by finite numbers of states and by clock-driven state transitions. So here, as the name indicates, the finite state machines. So the name indicates the finite state machines. We see they are characterized by the finite numbers. Okay, finite number of states. Only the finite number of states can be seen in the finite state machines, and the clock-driven state transitions. So the state transition, the occurrence of transitions between the state 1 to state 2 and from state 2 to state 3. The occurrence of state 1 and 2 can be observed with respect to the clock transition devices. Clock-driven transitions can be seen with respect to the different states. Then there are two different fundamental types of finite state machines. Okay, they are Mealy and Moore. We'll be discussing more about these two structures in the coming classes. So Mealy and Moore are nothing but these are the two different finite state machines. And here in this Mealy and Mealy, we will see how the output depends on how the output occurrence based on the dependency of the inputs based on the present or past. And also we will see how the transition takes place between the different states, okay, based on the clock. So here the next transitions and the output of Mealy machines depend on the present state and the input. So here coming to the it's like a gist you can consider. When it comes to the Mealy machines, we say that the present value Mealy machine depends only on the present state and the input. So only on the present state and the present input, the Mealy machines, the output of the Mealy machines is been observed. And the next state of Moore machines depends. So the next state of Mealy machines is only on the present state. Only on the present state and the present inputs, right? But when you compare with the Moore machine, so Moore machine depends on the present state and the input, but the output depends only on the present state. So here, in this Moore, if you observe with Mealy, if you compare with Mealy, it also has the present state and input, but the output depends. The output depends only on the present state. So here in the Mealy machines, the output depends only on the present state of the input. In both machines, the next state and outputs are formed by combinational logic. So here in this, both the finite state machines, Mealy and Moore, both the finite state machines, the output is the next state and the output. The next state and the output is observed, or else it's formed only by the combinational logic. Okay, so we know how the next state is formed. Next state is formed only just because the present state values and the present state output, right? So the Mealy and Moore machines, when you observe, the next state and output is formed by the combinational logic. So this is all about the sequential logic. So today's topic we have learned about the sequential logic. What are the sequential logic? What are the designing of the sequential machines? How the next state is formed and what is the present state? And how the outputs are, or else how the present state, how the machines, some machines are depends only on the present state of the value, present state output, present state input, and some machines depends upon the present state input and as well as the past output, the history of the inputs. And also we have discussed depends upon finite state machines, and the finite state machines are categorized, or else it has in more if you want to discuss, we have Mealy and Moore, and we have seen the comparisons between these two. And also we have discussed the state transition machines. State transitions, what is a state and how the state transitions takes place between these two. It all depends upon the memory the state is holding. and the output is observed only on the present value of the memory or else a past value of the history of the memories elements. And also we have discussed about the state register. State register is nothing but the memory, and that memory, the state registers, is nothing but the information which is present, the information is nothing but the which is coming from the next state and as well as the present state. It's nothing but the state register. So this is all about the sequential logic. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.